So you know how every time we visit the doctor and the first thing they check is blood pressure? But what exactly is blood pressure and how does physics explain it? My name is AB.
My name is Felix.
My name is Cyrus.
And our project, the physics behind blood pressure, explains how fluid pressure, resistance, and circulation works together in the human body.
In this presentation, we'll first explain physics concepts behind blood pressure and then demonstrate how blood behaves in fluids, and finally connect those concepts to blood circulation and then use a biogometer to measure blood pressure.
In this demonstration, we'll show the principles of pressure fluids with varying factors. Our first demonstration is a horizontal demonstration of resistance in which we punctured holes into the water at different diameters, with a small hole in the middle, medium hole on the left, and large hole on the right. As you can see, the bigger holes gave less resistance for the fluid to exit than smaller holes, which with the falling pressure exerted in the nature of liquids, we can still flowed heavily through the larger holes while the smaller ones filled up. The second demonstration is a vertical demonstration of pressure in which the holes of similar sizes were punctured. This demonstrates the effect the height plays in pressure. As you see, as delta height increases, so does the pressure. Remember the formula for fluid pressure. Height times density times gravity equals pressure. Since gravity and density are the same for each hole, that leaves height as the only differing factor, which increases as height does.
Hello, my name is Felix. Today I'm talking to you about the circulation of blood due to pressure. The circulatory system contains two main pathways, the pulmonary circuit and the systemic circuit. The pulmonary circuit moves blood from the heart to the lungs, and the systemic circuit moves blood from the heart throughout the body, which eventually returns back to the heart. These two circuits allow blood to continuously circulate throughout the body, but what actually causes the blood to move through these pathways? Blood moves through a circulatory system because of pressure differences. The heart acts as a pump which creates pressure when it contracts. As explained earlier throughout the presentation, blood naturally moves from areas with higher pressure to lower pressure. Because pressure is highest near the heart, blood is pushed through the blood vessels and throughout the body. Without these pressure differences, blood circulation will not occur. And as shown in these pictures, blood first enters the atria, which causes higher pressure in the atria. Now the blood wants to flow into the ventricles where there's lower blood pressure. Now that it forces the AV valves to open, causing the blood to flow into the ventricles, there is higher pressure in the ventricles. Now the ventricles contract, causing the semilunar valves to open to where there's lower pressure, which are the arterioles. Now that there's higher pressure in the arteries, blood wants to flow back into the ventricles where there's lower pressure, but it is stopped when the semilunar valve closes. And as blood flows throughout the circulatory system, the sizes of blood vessels also affect blood flow and pressure. Different blood vessel sizes create different amounts of resistance to blood flow. Arteries carry blood away from the heart under relatively high pressure. As arteries branch into smaller vessels called arterioles, resistance increases because the pathways become narrower. Greater resistance makes it harder for blood to flow and increase blood pressure. This is similar to the bottle demonstration with different hole sizes. The smaller holes restrict the fluid flow more than the large holes, demonstrating how narrower vessels increase resistance. After blood passes through the capillaries, it returns to the heart through the veins, which carry blood under lower pressure. And as shown in these images, blood pressure decreases when it goes from the arteries to the veins because, as shown in this image, the arteries have a narrower diameter and the vein has a bigger diameter for the lumen, and the capillaries have an even more narrower, which causes more resistance and higher pressure. Now for AB, he will continue explaining how a thermometer measures blood pressure with physics.
Hello, my name is AB Macias and I'm going over the physics of the sphygmomanometer and the physics behind it. So using a sphygmomanometer. On this slide, I'm going to explain how a sphygmomanometer is used to measure blood pressure. When you go to the doctor, the first thing they do is check your blood pressure. They check your height and weight too, but the blood pressure is like really important. So you know how they put like this thing around your arm? That's how they check your blood pressure. And this device, and it includes 4 main parts, which is the inflatable cuff, which is right here, the pressure gauge, the little bulb here, and the stethoscope so they can hear your blood pressure. The cuff is surrounded around the arm over the brachial artery. Yes, the brachial artery, which is the most major artery that carries blood through the arm. Then the doctor then pumps air into the cuff using the rubber bulb. As the cuff inflates, it squeezes the artery and increases pressure on it. When the cuff pressure becomes greater than the blood pressure inside the artery, blood flow temporarily stops. Then air is slowly released from the cuff while it does with the stethoscope. As blood begins flowing again, special sounds called carot cough, if I'm not mistaken, carot cough sounds can be heard. The first sound that is heard represents systolic pressure. Systolic pressure is the maximum pressure in the arteries when the heart contracts and pumps blood. As more is released, the artery fully opens and blood flow becomes smooth again. When the sound disappears, that measurement is called the diastolic pressure. I'm pretty sure diastolic pressure is the minimum pressure in the arteries when the heart relaxes between beats. Yes. Blood pressure is usually written as 2 numbers, such as 120 over 80 millimeters of mercury, or millimeters of mercury written as mmHg. In this example, 120 is a systolic pressure. 120 is the systolic pressure on the top, and 80 is the diastolic pressure at the bottom, which is 120 over 80. Blood pressure is measured in millimeters of mercury because older pressure measuring devices using mercury back in the day. Even though like modern devices are like digital and online, you can do it online. But yes, measuring blood pressure is very important because it helps doctors detect health problems such as hypertension, heart disease, and help you if you have increased risk of stroke. It's like so common used. We usually use it all over the United States or everywhere. So now I'm going over the physics of blood pressure measurement and the sphygmomanometer. The measurement of blood pressure is based on fluid physics and pressure differences. Blood behaves like a fluid moving through blood vessels, and pressure is created when blood pushes against the walls of the arteries. One important physics equation related to pressure is, right here, this physics equation. P equals F/A, which is pressure. Pressure equals force divided by area. In the body, the force comes from the pumping action of the heart, and the arteries provide the area where the pressure acts. When the cuff initiates, it applies pressure. It applies external pressure to the arm and the artery underneath it. Eventually, the cuff pressure becomes greater than the blood pressure inside the artery, causing the artery to collapse temporarily and stop blood flow. As the cuff slowly deflates, blood starts moving through the partially compressed artery. At this point, the blood flow becomes turbulent. Turbulent flow is irregular and chaotic. It is not stable, which creates vibrations and sounds called sounds, which the doctors hear through with the stethoscope. The first sound indicates systolic pressure because it shows that blood is just beginning to flow during the heart contractions. As more pressure is released from the cuff, yes, the artery opens up, and it's like more blood, more openly. There's more blood flow as it changes from the chaoticness to more laminar flow, which is like more smooth, more quiet. And that disappearing sound represents the diastolic pressure. Another important physics idea involved with physics is the gauge pressure. The sphygmomanometer measures pressure relative to atmospheric pressure instead of total absolute pressure. This means that the device measures the extra pressure created by the blood above the normal atmospheric pressure around us. Overall, The sphygmomanometer is a great example of how physics and medicine works together. It uses concepts like the fluid pressure differences, turbulent flow, gauge pressure to measure the force of blood moving through the body. And yeah, as you can see this diagram here, if cup pressure is greater than 120 mmHg, you can see that the artery is more closed, not allowing any blood flow. As the cup pressure is between 80 and 120, there's a little opening here. But if the cup pressure is less than 80 mmHg, then it's open, allowing blood to flow smoothly, which is diastolic. And this top here is systolic, I think, something like that. Systolic, yes. But yeah, and these are references to the group, and yes.